Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today I want to do a book review on this book here. And so there's something I kind of want to talk about, why I want to do this book review. I was working on this amplifier late last night and hoping to get up this morning, do a review on that, do a video on this. But as I was having my coffee, I was reading this and I thought, I need to review this book. When I bought it, I knew I wanted to review it, but there's a couple reasons why this one's kind of a special one. Even though I have a lot of other books I really love, this one is a topic that it's becoming more and more important. High-speed data, signal integrity type stuff. And I thought it was interesting they call it signal propagation because as a signal propagates through the air, let's say AM, FM radio, it's a radio wave, right? It's propagating across the airwaves to the receiving stations. And, kind of like how a wave in a lake will propagate across the lake when you throw a stone in it. Propagates. I just thought that was an interesting word to use. Instead of saying high-speed signal integrity, it's propagation. And because as that signal crosses the wire, it's not just, it's actually propagating, right? It's like a wave. So as current goes through a wire, there's a magnetic and electric field around that wire. And so that whole thing's propagating. So I thought it was just an interesting way to say it because that's the important thing to remember with these high-speed signals is that they do propagate. They're not just traveling across that wire, they're propagating across your board or across that cable. So there's these waves. And another part that I thought was interesting this morning is I kind of looked at the inside front cover here. It was just inside a couple pages. And there's a quote from Will Rogers. It says, even if you're on the right track, you'll get run over if you just sit there. So I thought, yeah, that's what I'm doing is I'm trying to keep moving. And that's why I keep on trying to learn. And that's why you guys are here too, I guess. So, right? So, yeah, we don't want to get run over. We might be on the right track. We're learning, but we want to keep moving. So I thought that was just a neat quotation. And I thought that was a neat use of the word propagation as it relates to this topic. So let's come over here, take a look at the book, okay? Oh, you know what? Before we do that, I want to show you my whiteboard. Try to turn this so there's no glare. Hopefully there's no glare on this. It's not a great picture, obviously. I drew it. All right, so what I'm trying to portray here is there's a guy named Roger Billings, and really smart guy. I think came up with the first hydrogen car. Anyway, he's done a bunch of things in his career. I think he's still on Facebook, and I think he's still interviewed, and he talks about things. I don't know. I mean, he's been around for a while, but he worked for Broadcom, or he was a consultant of theirs or something, and he did a demonstration that really wowed a lot of people, and it really made an impact. And it was called Interop. I think it was a conference back in the day, 1995. And it was like another 6 years before it was written about and talked about, I think. I believe that's how it happened. Okay, so back then they were working on 100 base T4. And later on, 100 base TX kind of won out. But they're trying to come up with a way to transmit data. And they're trying to, back then, 100 megabits per second was really fast. So they came up with this scheme of using 8 conductors, 4 pairs of wires, okay? And so what he did is to show that they understood how to transfer that data across wire. There's really some details you just have to be concerned with, and if you understand the physics of that, then you don't have to use fancy, expensive wire. So that might be a note for you audiophiles to spend a lot of money on cable. So let me just explain this. 100 megabits per second, pretty fast. So if these, let's say I got 3 bits here, 0 to 5 volt. Let's just call it that. Okay, so the rising and falling edges are very important, right? And so the slope of those things, if they're too, if they're sloped too much, say 10%, you got 10% here, 10% there, 20% of your signal is rising and falling. That's too much. So let's say it's only 1%. That'd be 100 times faster in frequency than this. So the rising and falling edges are what you want to be concerned with. Now, things like audio, is analog. You've got sinusoidal. You don't have those fast rising. So if you got 1 kilohertz signal, that's all it is. It's changing 1 kilohertz. This guy, it might be changing from high to low in 1 kilohertz or 100 megabits per second. But really, the frequency that you want to worry about is changing those ramps really fast. So your cable or if you're on the circuit board, those traces, all that stuff's very important on so you can keep that signal integrity, right? The integrity of that signal such that the sender, the transmitter is going to send a signal and the receiver is going to be able to decipher what that really was, right? So let's just go through this. What his demonstration was that caught everybody, that made everybody go, wow, was he had a spool of cable, okay, with these conductors in it, and then another spool of cable over here. In between those two spools of cable, he had this little demonstration thing. What it was 4-foot length of wires in about a 2-foot height frame, okay? And so there's just air and wires. All right, so it's pretty simple. The wires were actually barbed wire, rusted old barbed wire, just to make a point. So oxygen free, doesn't really matter. Back in the day, being an audio guy, I'd ask, the guys who are building cables and so on, like, hey, should we get some oxygen free copper, right? And they just look at me like, what are you talking about? What's oxygen free? So is it a thing? This guy's using rusted old barbed wire to make a point. This back in 1995, 100 megabits per second. Now, to be fair, each set of these wires is only taking 25% of that. So with the 4 of them combined, they're getting 100. So each set is taking 25 megabits per second. That's still super fast. So let's say it's 25 megabits per second. That's still 1,000 times faster than audio. More than 1,000 times faster, right? Now, just to even have a bigger comparison is, remember the rising edge. Let's say it's 100 times faster. So it's really 100,000 times faster than audio. So yeah, it means something. It's really hard to keep the integrity of that signal looking like this. You've all seen maybe where square waves start looking like sine waves. They lose their edges, right? Well, that's not good. The clock on the other side, the chip on the other side has a hard time determining where that clock is. Yeah. So when that clock's coming through, okay, so let's just say that the chip on the other side is expecting a 5-volt signal. So maybe let's just throw it out there, 2.7 volts is where he goes, oh, it just changed to high. So as it crosses over, if there's a slope there, it can be a little bit less determined exactly where that point is, right? I mean, if it's super fast, then as long as it's happening at the clock is locked in, you're going to be seeing it at the same spot. Otherwise, it looks like it's jittering. It's called jitter. The clock, it's kind of moving back and forth. It can't really lock in because, of that jitter. And then as it drops down, let's say it thinks, oh, 2.1. Once it hits 2.1, it's low. Well, the difference in those times, if there's a lot of slope, it's not happening at the same time. So there's a little bit of a jitter in there. So there's ways that they've worked around that stuff, but the best way to do it is to keep that signal. Well, first of all, you want to try to keep as much integrity to the original signal as you can, so it doesn't look sinusoidal, for one. Okay. So here you are. He's got barbed wire, 4-foot pieces of barbed wire, and the data transferred just fine, no problem. Because remember, in digital, even though some people, like audio people, might think a better digital cable is better, if it works, it works. and you can buy a fairly inexpensive cable. It's just got to be designed right, and it works just fine. When I bought my first high-def TV, I bought an expensive HDMI cable because I'm an audio guy. I got suckered into this cable stuff. And then my next TV, it came with the HDMI cable. It was even higher def than my first one, which was like 1K, I think. Then I went to 2K or something like that. And it came with a cable. And it came with a cheap cable. And I had my real expensive cable thinking like, oh, I'll put this on. And I'm like looking at the cheap cable, and I tried them both, and they both worked fine. I couldn't tell any difference because if it works, it works. So, yeah, I didn't buy any more expensive HDMI cables after that. So, anyway, cables have to be built correctly to keep the integrity of your signal. And if they're not, then they're just no good. You can't use them. So, here's the thing. This barbed wire, there's four, really, what this guy in the book is trying to say is he wowed people by this, and they were trying to show like, hey, we know what we're doing, obviously. So even if we use barbed wire, we can make it work because we know how to space these things correctly to make it work. And that spacing is really critical for a lot of reasons. Well, a lot. Let me say there's four things that what he's pointing out, okay? One thing is crosstalk. You know, there's that magnetic electric field on each wire, right? As it propagates through. When it propagates through, you don't want those waves cross-talking to this second set of wires. So you got to keep that distance. That seems kind of obvious, right? Distance. That's cure-all. Okay, so there you go. No crosstalk. That's one of the four things, okay? One of the other ones is high frequency. This copper carry that high frequency? Well, at this frequency, barbed wire is plenty fine. Skin effect was not an issue, okay? So, and that's pretty fast. And remember, those rising edges are the thing that's critical. And the barbed wire, it was the diameter of it, so on, no problem. Remember, it's all rusted and everything, still no problem, okay? So the third thing is signal delay. These are straight wires. Now, if they came and curved up, maybe the outside wire has to go farther than the inside wire. The outside wire would be longer, so there might be some time delays between those. But since they're straight, and the other part of that is the dielectric around them. They're in air. Now, let's say they're in a board, FR4 or something like that. I don't want to call it sludge, but you can imagine it's a little bit harder. The dielectric's a little different as the signal travels across it, okay? So the speed could be affected by that. But in air, no problem, okay? So crosstalk, not a problem. High frequency, can it carry a high frequency? Yeah. Skin effect's not a problem. And the impedance and so on is not a problem. They're straight. In this case, they're all straight. So the time delay was the same for each one, so there's no issues there, okay? So the fourth thing was the impedance. So we might know that when you're doing high frequency stuff like RF, for instance, it's 50 ohm, 75 ohm cables, right? For, say Ethernet, differential pairs, if these are each in, differential pairs, you might want 100 ohms. And in fact, for this 100 base T4, they used 100 ohms. So the cable was 100 ohm. It's 100 ohm on this. The reel on this side was 100 ohms. That side was 100 ohms. So it all matched up. And how do you make that match? Well, remember, that field that's traveling on this wire wants to have the opposite field on that one. So if they're placed really close, there's not very much impedance. They combine very well, so there's not much impedance, okay? As you bring this wire away, well, kind of like this set, how it's separated from this set, there's a lot of impedance here. I don't know, let's say mega ohm, 10 mega ohm, something like that. So that's why they don't crosstalk, because there's impedance. There's lots of impedance. So these wires, I think on his display, I'll show you the picture, but I think they look like a ½ inch to an inch apart to me. So it turned out that they had about 100 ohms impedance given that distance from each other, okay? So matched impedance. Now, for lower frequency stuff, some of those things are less concerning. Well, as speed goes up, it's more concerning. So for audio, for instance, when you're looking at those four things, the crosstalk, that's a thing. You want to keep signals away from each other. So routing your cables, you can keep your crosstalk down by just routing your cables away from each other, right? The speed, they're much slower in this, so the impedance of that cable, the skin effect. Now you're thinking about, well, I need the skin, it's going to go deeper into that skin, so I need a bigger cable to carry, depending on how much current you're carrying. So you just need to make sure your cable is large enough to carry that current, right? Because the skin, it's not going to be a thin skin, because the higher frequency, the thinner it goes on the edge, but lower frequency goes deeper inside, right? So you just need a cable big enough so these four things kind of cover audio stuff too. So crosstalk, keeping your thing separate. The high frequency, it's not high, so it's low frequency, so the skin's deeper, so you need a big cable. Delay's not an issue with audio, it's too slow. You're not going to see delays. Things are traveling slow, so it's not going to be an issue for delay. And as far as impedance goes, the impedance between conductors, usually you want to have them well coupled, and so you twist the pairs and that cancels, so it's really easy to make audio cable low impedance and work well. So yeah, audio is much easier than this high speed stuff where you end up with big thick books like this just to try to talk about how to transfer this knowledge into a circuit board. Okay, let's come over and look at the book. Okay guys, so that's what my book looks like with the sticker on it. I'm going to try to take that off. Alright, actually it doesn't look too bad. I thought I was going to have to work at this for a minute because I tried to take it off originally, and it's because the sticker is kind of torn in a few places that it doesn't, but most of it was coming up really easy, as you saw. So I was trying to take the stickers off so you could kind of read about the authors, but I'm going to have to work at this a little bit more. There's the Will Rogers quotation. And there's about 5 or 6 pages or more of the table of contents, so I won't bother going through all those with you. Okay, there's how you contact the author, and they have glossary of symbols. So now this book starts from fundamentals, okay, some math and some physics. Now this is a hand-drawn picture of what an eye chart might look like if you understand or seen those things. Essentially what that shows is the falling edge and the rising edge. If they're nice and square, this eye will be big and open, but if they start getting sloppy, this eye closes in, and that's the problem. So, but they're showing the spectrum right here. Here's 10 megahertz and 100 megahertz, so it's showing you the 100 megahertz clocking signals. So yes, so it's historical note. They talk about Nepper, where the term came from, John Nepper. So back in 1550 is when he was born, 1617 is when he passed away. But yeah, so a lot of stuff, up front, just magnetic permeability scaling, dielectric. So the first part will give you some background if they're talking concept of resonance. This is that famous Tacoma Narrows Bridge that just wiggled itself to death. So there's some of the math I'm talking about, resonances and Q factor, quality factor, things like that. So you'll see a fair amount of math and stuff just up front. Here's that picture of that bridge when it fell apart. And then it starts off with transmission line parameters. So that's where things start getting interesting, right? Alright, and this is the section where they talk about the barbed wire demonstration, showing Roger Billings there. This section talks about skin effect. They go into a lot of detail. They show how resistance gets graphed on a straight line, then turns inductive. And this is a pure inductive curve there. Again, they go through the basics and bring you through. So, a simple diagram showing the current going through a wire, going in that direction. You got the B field, the magnetic field in this direction around that, and then you see you have the eddy currents around each one of those B fields. And then this is an interesting page showing skin effect, and they show the frequency. Inductance resistance pretty much stays flat until you get out to about 100 kilohertz, right there where they start to change. And then 1 megahertz starting to look big. So at 1 megahertz and on, you're starting to get some real differences in impedance. But nothing, about 100K is where things are changing. And then how that field from one conductor can go into the field of the next conductor going the other way, and how they can affect each other. They talk about the proximity effect. Now, on a circuit board, they even talk about the surface roughness. And so it's really interesting. They don't miss anything. And then they get into how the dielectric affects the signal. And I'll show you something I really like. Often through the book, they'll stop and they'll say points to remember. And dielectric losses in transmission line scales in proportion to both frequency and length. So they have these, points to remember. So you can jump to the points to remember if you kind of understand these points, and maybe you don't have to go back and read that section. And then chapter 5, they jump heavy into PCB, printed circuit board traces, and they show you buried traces and buried vias and things like that. Microstrips versus strip lines. A lot of talk about that stuff. A nice diagram showing a signal, a trace going on one layer of a board, and on the other layer you have a VCC, or it could be a ground plane, but it shows how it couples to either power planes or ground planes. Another thing I like about this is they'll put boxes like this, bold print, saying, hey, important, and nice diagrams. And they also talk about, the victim and the aggressor. So you got this aggressor, the signal traveling across this way. You got one victim here, his signal came down too close. Same here, the signal went too close. So these guys became victims to this aggressor. And there's details like this, a coax cable coming into a board, say a strip line, or a microstrip. And so they're showing how this conductor in the center is tapered down to come in contact with the board. And then this box up here, to reduce parasitic capacitance, cut back the ground plane in the vicinity of the SMA signal pin. So you can see that done over here. And then dangling vias. So a signal comes across here, right? And it goes up this via. It's a blind via because it's cut off here. It comes over here, and it's going to travel up here to go this way. But this little via goes through the board down to this layer, so that's a dangling via, and same on top. Well, so then it comes over this way, and it comes up and travels on this way. I kind of went backwards from the diagram, but then this whole thing here is a dangling via, and those can also be called stubs. They go into some in-depth discussion showing as the signal comes this way and travels through the board to continue this way, you want to put a ground via here, so the current that's reflected, that's going the opposite direction of your signal, can come this way, can go up this way, and travel this way. So it's got because you always have to remember, you want to have basically a mirrored signal that's traveling the opposite direction as the signal you're looking at. So in this case, there's a ground plane here, so the ground current's going this way. It can mirror this trace. As it goes this way, it can be going this way, and then as it goes top, it's still going this way. So in this case, you're okay because you have a ground plane adjacent to each layer, so it works there. But over here, it went from one, there's a plane here, so it's coming across one plane, going through another plane, and traveling. So you have to have a connection between the planes. And that's kind of a 3D view, showing how that path is going this way, and meanwhile the ground currents are kind of, those paths that go around it are able to track the opposite direction. But then you also want to keep in mind this. So here is the aggressor, signals coming through, and it has a ground return right here, but there's a victim via over here, another signal coming up, and now this ground field that is being caused by this signal coming down is can totally couple into this guy. So you want to keep those things separate. And on this page, they show different pictures of keeping things separate, the victim from the aggressor, and so on. So this is an interesting set of pictures. They're showing a circuit, this big old beam here as a return path, right? So you got power source here, a switch closes. So they're calling this a transmitter. It transmits power to the receiver. It gets the power, but they're both referenced here. So you got this current path here, right? No problem. And they're kind of showing some impedance between the return of the power source to this plane that takes the ground plane to the other, receiver. So there's some impedance between these things, right? So then what they're showing is, okay, now you got the circuit, but now you add this other circuit, and this closes the same way. But now what happens when this closes, there's an inrush current here, and there's impedances here, some voltage drops, so you get a ground bounce. The return here is going to be a different voltage level, so this circuit here is going to see it that's connected to it. Where instead, first of all, if this power source came off, if the return to this receiver here came off the power source closer instead of off the ground plane, then that bounce is going to be kept here. The current path is going to be here. It's not going to pull current across this beam and cause this to be at a different voltage level. So this is still all basically a zero voltage level, right, where you want it to be relative to here and here. So this also has its own return path back to its power source before it comes back to the ground plane. But then if we think about a differential signal where we have a plus and a minus coming and the reference is somewhere in the middle, then both of these paths have the same impedance to this ground plane because it's returning, it's putting a 0 point right here, and when this switch closes, the power is going this way, but the impedance to the ground plane is the same. So if you're able to have a cable with a differential pair, you can do twisted pair. That works great. But on a circuit board, you can't twist the wires, so it really changes the method and how you keep common mode noise down. So this kind of diagrams what I was talking about before, how people like to, on a circuit board, have traces run along together like a nice highway where they can pull them together. And you don't want to do that. So this guy here, let's say he's an aggressor. He's maybe some circuit that's going to some chopper, who knows what. And he could be coupling to these two clock signals. Well, this clock signal here, he's going to have more coupling to because he's adjacent to it. And less coupling, but still some coupling to the other clock signal because those two clock signals are going to be ran together, right? So it's going to interfere with both, but in different levels. So it creates a differential, voltage there. So right here, you don't want to have two reference planes with a differential pair or a circuit crossing over two different reference planes. That's a no-no. And like say, when the current's going this way, you're going to want a return current going underneath it or next to it. And as it goes this way, you do have one, but it can't cross this path, so it kind of goes against this. As this one comes down, it follows this one, but then it goes over here and says, okay, I'll follow this one back. So that you can kind of see that happening on both sides. But in between, he calls it the U-turn zone. It's kind of interesting. I haven't heard of that before. And then over here, here's that 90 degree. That's a no-no. So now it's 245s is what a lot of people do. But this curved thing is actually the better way to go. So as I say, he does talk about strip line and microstrip both a lot. And here he kind of shows pictures of both and how they couple to the fields or to the planes and adjacent layers. And when he talks about EMI, and I talk about this too. I talk about having a sheet. You think about a sheet, like your ground plane's a sheet laying across your bed, like your bed sheet, right? And you want to stitch it down. You don't want the wind blowing your sheet, so it's waving around. And right here, he's showing the impedances of this ground plane, basically. And where bypass capacitors, it's stitched, it's low impedance, it's pulled low. And then over here, you see these mountains where there's nothing around it stitching it to the other layer. I can see right here, this looks like a bypass cap, right? A bypass cap. You can see where the bypass caps are pulling it down. So, you know, that's one reason bypass caps are kind of spread across a ground plane, is to pull that ground plane down to keep it nice and snug to the bed, to the rest of your, you know, layers. So, you know, that's the way I kind of talk about it too, and I found that interesting to see this here. And I thought I'd finally show you this. This is showing different kinds of ways when you're trying to, you have two traces, you have to put some wiggles in one to make the length of that trace the same as another trace, so you have the timing of those traces is the same. You might have seen these. He talks about the differences of using big wide ones, you know, different shapes and different amounts of wiggles, and the benefits of the different ones. Okay, so this is a really important section. I'm going to spend some more time reading this because this is something of interest. All right, guys, so what do you think? Pretty cool book. Yeah, I definitely recommend this book. The Martin Graham, I know less about him. Howard Johnson, I've seen his stuff. When I've looked up differential pairs, how to lay them out on circuit board, his name pops up. There's been a number of people that are well respected that you know, quote him. So yeah, and yeah, like I said, I like that, the use of the words and that first quote. So you got to keep on moving ahead, keep on thinking, and keep on learning. So hope you guys like this, and let me know in the comments if there's sections of that book or other books I've done, or what you think about book reviews. The digital books are definitely easier to show you guys pages of it. So yeah, I don't know. Let me know what you guys think, and appreciate you watching. 2 thumbs up my patrons as always. Really appreciate you guys. And hey, we'll catch you next time. I gotta get back to this Class A amp.